Okay, good evening, everybody. Welcome. And
Evening.
We're going to start now. So, Dr. Pierre Cilliers is from SANSA. He's one of the country, I don't know, maybe the world's big boffins on solar weather. So we look forward to a very interesting talk on global experts on what happens and whether we must find a tunnel to slip in under the ground and so on. All this solar explosions that are going on at the moment. So, Peter, would you perhaps just like to say a word of introduction, or can we go for it?
All I can say is that Pierre is a very exceptional person. I met him he joined from the University of Pretoria about 10 years ago, when I was still at SANSA and was called the Hermanus Magnetic Observatory. In a very short time, Pierre established himself as one of the leading figures nationally as well as internationally in the field of space weather. And so solar radio burst is one of the physics driving forces behind space weather, and tonight we're going to hear much more about those things.
Okay, so we're very privileged to have one of the experts, real experts on the subject, and we look forward to hearing this presentation. Thank you.
Thank you very much. Now, I must give Peter credit. I think he played a role in getting me to SANSA, because I came down here to Hermanus every year since 1988 to visit my wife's family who had retired in Hermanus. And every year I went back to the University of Pretoria with a sore heart and thought, isn't there a job for an engineer in Hermanus? And then one year I spent some time at the Magnetic Observatory and asked them, is there anything that I can do here that you would find useful? Because I was looking for a place to do my sabbatical. And one of Peter's colleagues there showed me some interesting stuff that they were doing. And he said, we're collecting this data, but we don't really know how to use it to characterize the ionosphere. Would you be interested in checking this out? And I spent a year doing just that and establishing a new research field at SANSA using GPS signals to characterize what goes on in the ionosphere. And then I went back to the University of Pretoria, and a month later, the then director called me and said, would you please come back? We've got lots of interest in this topic now. I've just come back from a conference, and this using GPS for ionospheric characterization is the hot topic. We would love to have you continue the work. And so I applied for the job and I got it. And I am delighted. I've been here for 20 years now. We came in March of 2004 full time. So yes, I'm a research fellow. I'm still, after retirement, a contract member of the space weather team at SANSA, developing new products on space weather and investigating impacts of space weather and trying to understand space weather. And what I will present this evening is a little bit of a scope of some of the things that I'm involved, but the focus eventually will be on solar radio bursts and what it means and what it does and why we need to be concerned about that. So thank you very much. So those are a few of the things that I'll be talking about. Can we get rid of that at the top? Let's try. Let's see. Okay. Awesome. Yeah. So we're going to talk about what happens when the sun sneezes. What is space weather? Show you some recent space weather activity. We are living in exciting times and there's lots of it going on. What impact does it have on various technologies that we use in everyday life? And then focus on what is a solar radio burst, the topic of my presentation, and how do we measure them? And what does it tell us about the sun? And what are its impacts on the Earth? Good, let's go. So this, what happens when the sun sneezes, is a term that derives from our late director, Dr. Leanne McKinnell. She used to say, when the sun sneezes, the Earth catches a cold. And the sun sneezes in the form of flares. There's explosions on the sun. Lots of matter gets flying as when one sneezes. In fact, it's in the form of billions of tons of hydrogen atoms that go flying towards the Earth. And then some things happen on the Earth if that sneeze is directed towards the Earth. So let's start with the sun. if you've got a telescope and you've got the right filter to look through so that you don't damage your eyes, you may today see this picture. That is the white light image of the sun. And what you see there as dark spots are known as sunspots. They are regions of great magnetic activity on the sun and usually the origin of flares. Sunspots are not solar flares, but some sunspots are the regions from where the flares emanate. And it's a region of magnetic turbulence, which has the potential for eruption into a solar storm. Today's sunspot count is 146. So not all of those are as bright as the ones on the bottom right there. All of the sunspots on the visible side of the sun are numbered by NASA or by SWPC, American Space Weather Prediction Center. And so we can refer to particular sunspots as having been the region from which a particular flare emanated. And if the sunspots are in this region, we call them geoeffective. Because if flares emanate from those regions, then it's likely that they will intercept the Earth. Not all flares intercept the Earth. Some of them go above, some go below the Earth, some go before and some after the Earth. But the ones that do come our way can create pretty pictures, but also create havoc. Sunspots are some of the oldest evidence of activity on the sun that waxes and wanes. And what you see there is just a record of the yearly average sunspot number from the year in which Galileo invented the telescope until recently. And you can see that there is a cyclical repetition of the number of sunspots. And right now we are close to the peak of the current solar cycle. We are in solar cycle 25 now. And that means for 25 11-year periods, we have been counting sunspots. However, there was a period in the 1600s when there were no sunspots visible. It was known as the Maunder minimum. And it was not because they couldn't be seen, they were just not there. Because prior to that period, they could count the sunspots, but then there were just none of them visible. And that was also known as the Small Ice Age in Europe. And for 70 years, it was extremely cold in Europe. The prediction panel of the Space Weather Warning Center in USA tells us that we are approaching the peak of solar cycle 25. That's the last part of that previous curve that you just see there. And we are now approaching the peak of solar cycle 25. And it's already been predicted that the peak may occur earlier than previously predicted. Currently, the prediction says we will have a maximum sunspot number of 115. We've already surpassed that. We've had a number of surprises on the solar cycle so far. And one of them was this flare that was recorded on the 3rd of October. However, earlier this year, on the 10th of May, we had a storm was known as the Mother's Day storm, simply because it fell on Mother's Day. And I'll show you some of the evidence of that one. But I'm going to play a short video here that just shows the sequence of events when there's a flare on the sun. It doesn't have sound with it, but I just must make sure that I can now play this video. Go back to this. Okay, so there we go, and play that again. So this constant stream of particles from the surface of the sun, called the solar wind, gets enhanced significantly when there is a flare from one of these active regions coinciding with a sunspot. That solar wind brings a bunch of particles to the Earth. The Earth's magnetic field deflects most of that around the Earth. That's why it's called the magnetosheath. It sheathes the Earth, but those particles carry a lot of energy to the downwind side, and then we get what is called a reconnection. That energy gets drawn back by the magnetic field lines into the Earth's atmosphere, and what we then see as a result is the aurora in the northern and southern hemisphere. So it's actually energy that has been passed around the Earth, coming back from the tail side, drawn by that reconnection of the magnetic field lines, which act like rubber bands, and they pull those particles back into our atmosphere. And the colors that one sees in the aurora is the light given off by our upper atmospheric particles, nitrogen, oxygen, hydrogen, that then get excited by these particles coming into our atmosphere. And when they return to the normal condition, they give off the light that we see as the aurora. And so aurora happens at both poles simultaneously, as you can see on this. There we go. So that was this little video that shows the events that follow a solar flare. Now I'm going to talk about what actually happens in that process. The first thing we see is the flash on the sun. That reaches us within 8 minutes. Those are electromagnetic waves traveling at the speed of light. And so when the first time that the flash on the sun was seen and connected to something happening on the Earth was by Lord Carrington, 1859, I think. It's called the Carrington event. And for many years, it was thought to be the most extreme event ever observed. In 2012, there was another Carrington event. Fortunately, it didn't come our way. It was a flare of the same intensity as the Carrington event, but it went the other way and it was observed by satellites on the other side of the sun, not coming our way. So the flash on the sun is our first evidence that there is something that may come our way. But together with a light emission, there's an emission over the whole electromagnetic spectrum, including X-rays and radio waves. And our focus today will be on these radio waves that get emitted, but they're all electromagnetic waves. They all travel at the speed of light. Some of them last longer than others. The flashes are very short duration. The X-ray emission can carry on for an hour or more, and the radio noise keeps on going for quite a while. At the same time, the sun emits this cloud of particles, which we call the solar wind. And those particles travel at very high velocities. They reach the Earth within a day to 4 days, depending on their velocity. They travel at anything from 400 kilometers per second to 2,000 kilometers per second. And when we see that flare on the sun, we can also make an estimate of what is the propagation velocity of those particles, and we can estimate how long it will take for those particles to reach us. When those particles enter our atmosphere, they increase the conductivity of our upper atmosphere, they increase the currents in the upper atmosphere, and those currents in turn generate magnetic field on the Earth, and that magnetic disturbance is called a magnetic storm. And so there are several ways in which these events can impact our technologies. This light itself will possibly not do much more than cause some increased flash on a telescope, but the X-ray emissions cause an enhancement of the ionization of the upper atmosphere and can severely impact radio communications because of the increased ionization. And then the radio noise that I will talk about more in terms of solar radio bursts. So I'm not going to focus so much on the energetic particles and magnetic storm in this presentation, but they happen also. But I had to show some aurora, because for the first time in history, as far as I know, aurora was seen from land here in Southern Africa. The first time we saw aurora was on the 10th of May with the Mother's Day storm. We didn't think we'd ever see that again. And within a few months, we saw that again. And these are just some of the images that came in. This one is taken from Cape Point, and this one is taken at Simonstown, and this was taken from Cape Agulhas. There's the Cape Agulhas block, and this was someone sent it in from Strand. And yeah, so it's just amazing that we could see the evidence of the impact of these particles in our atmosphere. Obviously, you're looking south in all these cases, because what happens is if there's an intense storm, the region where you can see the aurora expands equatorward, both from the North Pole region and from the South Pole region. And so they could also see aurora in Texas and other locations in the United States, which are much closer to the equator than where normally aurora is observed, like in Canada and Scandinavia and other northern places. But yeah, that is actually a radio emission, but that's light emission at the upper end of the radio spectrum. So it doesn't quite qualify as solar radio burst, but it's just beautiful. And that was the earliest evidence of something happening on the sun that was unusual. And it's been recorded in Babylonian times. There are some Babylonian scripts that refer to this bright red appearance in the sky that lasted several hours, and they didn't then know what it was. Now we are fortunate to better understand that. So that was the beginning of the understanding of space weather, but there's a formal definition of space weather which we normally pose, and that says that space weather refers to conditions on the sun and in the solar wind and in the magnetosphere, the ionosphere, and the thermosphere that can influence the performance and the reliability of technological systems and can endanger human health. And we have to say that because even though those particles won't zap you on the surface of the Earth, the aurora stops at 100 kilometers. That's when all the energy of those particles have been absorbed by our atmospheric gas. So our atmosphere is one of the shields that we have that protects us from these harmful particles from the sun. If you're in a satellite, or on the if you're in space and you're on the International Space Station, that's not the case. Then those particles do impact you, and you can get radiation sickness, and you can get damage to the electronics on the satellite, and that happens. But fortunately, down at 100 kilometers, all of that energy is absorbed. But it can endanger human life in cases where critical technologies are affected, or when humans are exposed to radiation associated with solar flares, particularly when you're out in space. Okay. The first recorded space weather event was on the 1st of September 1859, when Lord Carrington talked about this flare, and he made some postulate about what it was, because soon after seeing the flare, there were some magnetic disturbances observed in London. And some people started making the connection, and he said, no, one swallow doesn't make a summer. Maybe this was an unusual coincidence. We can't really connect it. But by 1892, the Royal Society presidential address by Lord Kelvin said, it seems that we may be forced to conclude that there's some supposed connection between the storms on the ground and the sunspots. And that the agreement between the periods is mere coincidence. He didn't want to believe that they were connected. So he was also saying one swallow doesn't make a summer. But by November 1905, Prof. Maunder, after whom the Maunder minimum is named, said, we can no longer say it was a coincidence. There's definitely a link between the things that happen on the sun and our magnetic disturbances on the Earth. So let's look at some recent space weather activity. Just on the 2nd of October, late evening on the 1st of October, almost midnight, we had an X-class flare on the X-ray scale. Now, one of the emissions that I've mentioned was the X-ray emissions from the sun, and that's usually an indicator of how intense that storm will be when it reaches the Earth. So our categorization of storms is on this scale, A, B, C, M, and X, with X being the most intense storms. And you can see the flux density there in watts per meter squared on the left-hand side of the X-ray intensity that is received from a satellite that observes the sun 24/7 and measures the X-ray intensity. So we had an X-class flare, and this makes us sit up straight, because then there is a possibility of some significant impacts, as we have seen with the aurora that followed this X9 flare. And so these are the two flashes associated with that X7 class flare on the 1st of October, and the X9 flare a few days later, when that same sunspot group flared again. So you can see that the sun has rotated a few degrees during that period, and that sunspot region was very active and flared a few times after that, not every time with the X-class flare. Now, one of the impacts of this increased radiation, and I think if I stretch the definition a little bit, one can call the X-ray flare also a form of solar radio burst, since X-rays is a form of electromagnetic wave, is that we have this increased ionization of our upper atmosphere on the sun side of the Earth. And when the atmosphere gets ionized, it gets more absorbing of radio waves in the high frequency range of 3 to 30 megahertz. And so this is a map of showing the highest frequencies affected by at least 1 dB of absorption. And so what you can see on the scale is that 5 megahertz had 30 dB of absorption, and up to 35 megahertz, there was at least 1 dB of absorption of the radio waves in the HF band. The impact of that is that ships to shore communication, which is usually done via HF radio, and long distance communication from control tower to airplane when satellite communication may not be accessible, is done in the HF band. And so that means that sometimes planes cannot fly because the FAA rules say you always have to be able to fall back on HF radio when there's no satellite communication. And so planes that would have come into Africa at this time would have had to decide whether they were going to wait a while, because this fortunately doesn't last very long, about 1 hour and 8 minutes in this case. So planes can be delayed by the possibility that they will not be able to make HF communication. That's one of the impacts. A week later, we had 4 X-class flares. This now goes on to the 7th of October, the 9th of October, and in this week we had 4 X-class flares. So things are picking up, and these flares have a significant impact on GPS, among others. This is one of the flares that was coming from the northern hemisphere of the sun, the X 1.8 class flare, which left the sun on the 9th of October, close to midnight. And so by the time close to midnight was not our daytime, so it didn't affect us, but it had a severe impact in Indonesia and Australia, where, again, up to 35 megahertz communications were severely attenuated. Now, let's talk about some other impacts on technologies. From the early days of observing solar cycle, there was evidence that some things on the ground have some connection with the solar cycle. So in the 1800s, the telegraph system was already working in various places in England. And they were noticing some strange noises on the telegraph following such solar flashes. And they said, well, you know, what's going on here? At one time, they thought it may be the enemy that is now trying to deceive you by making whistling sounds on the telegraph or disturbing your telegraph communications. So there were disturbances noticed continuously following that. Then in the 1900s, they picked up on radio disturbance, either suppression of the radio or noise on the radio or fading of the radio signals. And then in the 1950s, when we got satellites into space, several satellites had outages during these storms. And so the impact on technology was noted very early on. And one of the most severe impacts was on what was the Quebec storm? There was a big storm that put out the power systems in Canada. It's also known as the Quebec storm. And the Canadians were without power for 9 hours. And for the Canadians, that's much more devastating than for us that have to deal with load shedding. And so, it affected communications and satellites and power systems. So here's a nice summary of some of the effects of space weather on our technologies. I've already mentioned the effects on people in space, astronauts. Simultaneously, there can be damage on all of the electronics and the solar cells in space. And if there's disturbances on satellites that may use the magnetic field of the Earth for orientation to keep their antennas pointing towards the Earth, and the magnetic field then suddenly fluctuates, this satellite will start moving around to keep its antenna facing the Earth and burn up all its fuel and shorten the lifetime of the satellite significantly. So that's effects out in space. Then the ionosphere, this upper ionized part of our atmosphere, gets disturbed because of the particles coming in, the conductivity increasing, and also the formation of what is called patches and bubbles of low, bubbles being areas of low density that percolate from underneath upwards, and patches of high density that typically form when the ionization on the night side that's associated with the aurora streams over the poles to the day side, and then we have patches of higher density. So there's fluctuations in the electron density, therefore changes in the velocity of the radio waves traveling through this ionosphere. And if there's a change in the velocity, that gets evidenced as disturbances on whatever you want to do with the signal. And so that includes GPS receivers, because our satellites that give us the signals from which we derive our position is out at 20,000 kilometers. The ionosphere ranges from 100 kilometers to 1,000 kilometers. And so those signals have to come through the ionosphere. And when there's disturbances like these, it causes errors on the GPS. And that has happened this week. And I'll tell you a little bit about that later on. People called us and said, we've got problems with GPS. And we said, yes, we know. We've got problems with space weather impacting us. One of the other evidences of this is that long-distance communications using the ionosphere for refraction, for ship to shore and for aircraft to their control towers, that gets affected because now the ionosphere is disturbed. And so the frequencies at which you need to operate will change so rapidly that you can't update it so fast. And so there's fading on the signals and people struggle to communicate on HF radio. Cellular phones get affected by solar radio bursts, which means at the time of the flare, radio waves in the band of cell phones, which is the microwave band, 1 to 2 gigahertz, suddenly increases in intensity to the point where the repeater stations get saturated and your call just does not feature anymore going through that repeater station. And so your call gets interrupted. That's been noticed, personally experienced. I was driving to Stellenbosch to go and give a talk about space weather, and I'm telling the people I'm on my way, and I couldn't get through because of the constant interruption that we had early that morning as I drove to Stellenbosch. Fortunately, I had someone else who was doing the driving. I just had to try and get the calls. Then electric grids is one of the few cases where we have permanent damage due to space weather storms. Satellites get deteriorated, the solar panels get deteriorated permanently, but not a complete wipeout of the solar panels. But if we have an impact on a power system, we can have some of these power transformers that fail. They are very expensive to replace. We've had that happen in South Africa in 2003 when the 6th largest storm in history struck the Earth. We had a severe damage to several of our high voltage transformers, which all failed within the next 8 months. And the evidence was clear that that damage that was incurred on the 31st of October of 2003 was the cause of early failure of those transformers. And then solar radio bursts also can interfere on radar because radar also operates in the X-band. And there were some very interesting events that were associated with such radar impacts of solar radio bursts. So my focus of my talk is on this event and its impacts on the Earth. So what is solar radio? Solar radio burst then is this energetic solar radio emission within the radio band, and it has an intensity that surpasses the ambient solar radio emission. So there's always this streaming radio emissions from the sun. And I initially thought that, yeah, that's why we that's where I have some trouble doing radio astronomy. And then I recognize you can't do radio astronomy during daytime because the solar radiation during the day just so much exceeds the radiation that you're trying to get from stars much further away than our sun. That there's no way that you'll be able to distinguish a stellar source of radio emission from that coming from the sun. So yeah, we do radio astronomy at night, even though we're not looking at light, but radio. And so if the solar radio burst exceeds that level of solar radiation, we call it the solar radio burst. It's of particular interest in plasma physics because these emissions from the sun is actually a symptom of various processes occurring on the surface of the sun. And the type of flare and how the frequencies change during the flare is giving us some clues as to what happened on the sun. And during this, and the radio waves are formed because during this process of plasma emission, waves are created in this high frequency band by these energetic electrons being accelerated in what is called the shock waves in the solar corona and associated with coronal mass ejections. So at the same time that we have this emission of large quantities of particles, we also have these shock waves that accelerate the electrons and then cause radio waves over the very wide spectrum. So this was taken from a paper by Loris Nip about the May 1967 Great Storm and Radio Disruption event. And a few more of my pictures will come from that paper that was written about an event that almost caused World War III because of a misunderstanding of what was happening. So there's the X-ray flare that I've mentioned before, then the coronal mass ejection, which lasts for minutes to hours, then the coronal mass ejection and solar proton events, when those protons come to the Earth, can carry on for several days. And when it reaches the Earth, we have this magneto-ionospheric storms, which can carry on for hours to days. The solar radio bursts, shortened SRBs, have various categories because of the way that the frequency changes over time. So the solar radio is not on a single frequency, but as these various energetic levels of the electrons emit radio waves, the solar spectrometers, about which I will talk soon, detect the spectrum, and they can show that over time the spectrum changes, and how that changes helps us to recognize what happened. So there are so-called type 1, type 2, type 3, up to type 5 solar radio bursts. There's a description of their spectral properties, whether they're rapid enhancements of a narrow bandwidth, whether there's a gradual drift to lower frequencies, often accompanied by harmonic components, or a rapid enhancement with a very abrupt drift in frequencies. How long these last is revealing to us. The frequency spectrum over which it occurs is very revealing to us. And this is the mechanism of solar origin that it helps us to understand. Likewise, type 4 is a moving stationary change, a moving stationary continuum that can last for several hours, sometimes up to days. It's over the band from 20 megahertz right up to 2 gigahertz. And yeah, so the moving ones last is in this frequency band, the stationary ones that last for days in the band 20 megahertz to 2 gigahertz, the continuum short duration 25 to 200 megahertz. And it is evidence of flares on the sun, proton emissions, prominences that have erupted, and proton emissions from the sun. And then the last one is the type 5 emissions, which are also indicative of active regions with very short duration. Now, why is this so important? When we have the benefit of internet working, and we can get these beautiful pictures from NASA that shows us what their satellites are visually capturing or capturing via instruments on the satellites, we know what happened on the sun. And we can see where the solar flare was. And we can see what's the velocity of the solar flare. But one of the technologies that is affected by solar flares and these radio bursts is the internet. And if we don't have internet, we don't see the flares. and we cannot estimate the velocities. Yet the solar radio bursts allows us to do a lot of that from looking at the spectrum of solar radio bursts. So we've got our own solar radio burst detectors here in South Africa because we need a backup for all those beautiful pictures that we get from NASA. And so I'm going to talk about how we measure that. But first I'm going to talk about impacts on navigation. As I've said, the radio signals coming from the sun is in the same band as GPS. And so it causes saturation of the GPS receivers. And so the receivers cannot do what they should. And it can affect communication also, because they also use that band for communication. And if you are on autopilot for your landing system and you operate in the band 30 to 300 megahertz, there will be errors. And these have been reported. And these are quoted from papers published. But it came very close to home just last week. People who were running a drone competition, that's where they have certain places where the drones have to fly in minimum time, just like a race through some loops and hoops and so on, and it's all mapped by GPS. And so they programmed the drone to fly this route. And they called us and said, guys, we've got problems. We can't get the drones to fly as they should. And we want to run a competition, and the people are complaining and saying someone's jamming us and whatever. What's going on? And we said, guys, you're quite right. There is a very strong flare, and wait a few hours because otherwise you will lose a few drones. And yeah, within a few hours, they could start their drone competition and fly all these kinds of fancy tricks with drones based on how their GPS guides them. Air traffic controllers may be severely hampered, as happened in 2015, when there was air traffic control ground radar disruptions in various countries, including Greenland. They shut down the air traffic and said, don't land somewhere else because we can't land you here because we can't see where you are because of the disruptions of the radar. Radio altimeters, that's the instrument used by the plane to measure how high it is above the ground, operates by sending a radar pulse downward and measuring the time that it takes to come back to the plane. And then from the velocity of light, estimating how high the plane is above the ground. However, if the sun is close to the horizon, that instrument itself that receives the return signal will pick up the solar radio bursts. And also, if that solar radio burst gets reflected from the ground, it comes together with that signal and causes disturbances on the signal, and can give rise to large errors, as was here calculated by my student who did a PhD on this stuff. And if you have solar radio bursts on the order of 10 to the 4 solar flux units, the error on the height estimation goes up to hundreds of meters and more. Mobile phones. Base station has these antennas that points down to the ground, because that's where most of the people are with mobile phones. But the beam is a wide beam, so that it reaches quite a large area. And so if the horizon is within view of this antenna, and the sun is just rising or setting, then a solar radio burst will just impact your mobile phone communications and saturate the amplifiers and cause interruption of calls. The mobile phone companies don't want to tell us how frequently that happens. I had a student who wanted to do a master's degree on saying when the vulnerabilities, how frequently does this happen. We really struggled with the mobile phone companies because they said, no, won't tell you, because ICASA will then tell us that we are not delivering up to standard, and they may take away our license. So we know that it happens, but we can't get statistics on how frequently that happens from the mobile phone companies. And then this was the event that almost started World War III. And Dolores Knipp wrote this up in that paper in Space Weather 2016, that on the 23rd of May, a multi-site, multi-antenna radar system, and this was during the Cold War days, was operating in various sites. And an intense, never before seen solar radio burst in the X-class category had a significant flare. And this flare was extremely high. It was 300,000 solar flux units at 606 megahertz. And at 10.7 centimeter wavelength, it was 8,000 solar flux units, which is kind of the top of the range of intensities of solar radio bursts. And NORAD, the American group that monitors anything that goes on in space that may be a threat to the American satellites, saw that there was something very funny happening on these radars, and they thought it's the Russians jamming the radars and trying to sneak in. And they got their bombers all fired up, and the pilots were sitting waiting for the command to fly and go and bomb the Russians. Fortunately, there were some space weather observers that said, whoa, wait. This is a space weather event. And those bombers didn't take to the skies. But there were some of the pilots who actually sat in those bombers that told the story to Dolores and said, we were ready to fly. So solar radio burst is serious. How do we measure them? There are two networks of these instruments to measure them. The one is known as the eCallisto, and SANSA has the eCallisto antenna. And then the other one is called, I'll get to it. So eCallisto is a network of solar radio spectrometers. So they simply measure the radio waves coming from the sun over a wide band. And these are the locations of these solar radio monitors. This is the eCallisto network showing that it's all over the world. And we had this antenna installed at SANSA a few years ago. It's a log periodic antenna. It operates from 270 megahertz to 8 gigahertz. It was pointing along the average elevation of the sun during the day. And it was supposed to tell us when there's something happening on the sun when we don't have internet or we don't have the means of looking at those images that otherwise would come from SWIPSI. That antenna has now been replaced by a rotating antenna, a 21-element log periodic antenna designed by a master student at SANSA, who worked at SANSA. It's now sun tracking. So this antenna points towards the sun at sunrise, and it follows the sun till sunset. It's again a very wideband antenna. It goes 52 megahertz to 1.3 gigahertz and records data from sunrise to sunset every day. And this is from a thesis of my student who did his PhD on this topic. Then the other one is the RSTN network. I forgot what was the abbreviation, but there are 4 of these RSTN nodes that supply solar radiation burst observational data. And there are these 4 locations around the world. And the data from these receivers are available for public retrieval, if you have internet, to go and look at what happened in particular bands on those receivers. And this is typically what you would see. They will show the period before the radio burst, what was the intensity of the flux, radio flux in each of these bands from 200 megahertz to 15 gigahertz, and then how that changed rapidly at the time of the solar radio burst and for how long there were disturbances after that. So you can see the lower frequency disturbances last much longer. They may even increase after the solar radio burst, whereas the higher frequencies decay within a short time after the burst occurred. But these are the frequencies at which radio aviation communication and navigation takes place, and so they can seriously be impacted. So what is the significance? Well, there have been opportunities when our own instruments were the only ones that detected the solar radio burst. And so this was one of those occasions when it was only us and I think Greenland that detected the solar radio burst. And what you typically then see here is at a particular time, there's an increase of intensity at a particular frequency. And this was then from 2 different sources, two different frequencies in the spectrum. And you can see how long that solar radio burst lasted. It was a type 4 radio burst, which is characteristic of eruptive prominences and shocks and flares on the sun. This one was a unique one. We were the only one that detected them. Of all the 25 or more Ecolisto receiver stations, only SANSA picked this one up. It was a long duration, 1 hour long solar radio burst that had significant impact on aviation, navigation, and communication systems. And it was also a type 4 burst. And there you can see the typical way in which the frequencies change with time. So this is an increasing frequency with time. This is a decreasing frequency with time. And it is these characteristics that allow us to infer what was the cause and the velocity of the solar wind eruption. So I just wanted to show a picture of our Space Weather Center where we do this kind of work and issue alerts and warnings for the various users of technologies that may be impacted by space weather. And we would like to invite you to come and visit us there if you haven't already done so. On a Wednesday morning, we have open to the public opportunity, and we take you on a tour and show you what we do there. And then I'd just like to express my appreciation for my student, Sarah McKee, who recently finished her PhD, and she wrote up much of what I presented to you. She was invited to go to the 73rd Nobel Laureate meeting in Lindau in Sweden in July this year because of the outstanding work that she had done on her PhD, among others. And then just my colleagues, John Ward, for some photos that he gave me, and the Space Weather team for some of these images of recent solar activity, and many of my colleagues at SANSA who contributed to my understanding of space weather. So thank you for your attention. Yeah, the Bible talks about the sun on many places, but I like this one. It says how clearly the sky reveals God's glory, how plainly it shows what he has done. Each day announces it to the following day, and each night repeats it to the next. No speech or words are used, no sound is heard, yet the message goes out to all the world and is heard to the ends of the earth. God made a home in the sky for the sun. Thank you very much. We can entertain a few questions, I presume.
Can I kick off with one quickly?
Please.
On your last bit, where you say, in the one thing, SANSA and Greenland were the only ones to pick up the signal, and the last one was only SANSA. What do you attribute that? Have you got better equipment, or were other people asleep? Or
no, you can only see it on the sun side, right? So that solar radio burst will not be visible on the night side because the sun's.
So it's a longitude.
It's a longitude dependent thing, and I think that was the case. That not all of these Ecolisto receivers are 24/7 operational. And it just happened at that time, ours was the only one.
Okay. Anybody else?
So, because it's pursuant to that, so what is the collaboration as the sun is moving and these occur between different countries that are on the dark side versus the sun side?
Well, it's one of the reasons why we have these observatories around the globe, so that people can anticipate effects that happen on the sun side. And as we are moving into the sun, we may know that there is a flare ongoing and there may be some impacts as we move into the sun.
So all of them, everyone's speaking with each other and sharing their information.
Yeah, there are, SANSA in Hermanus is one of 24 regional space weather warning centers, one on each continent, and managed by the International Space Environment Service. And so every morning before we issue our bulletin of what happened in the past 24 hours and what's going to happen in the next 24 hours, we talk to several of the other space weather regional centers to understand what happened in their region and inform the others what we are seeing. So some of it's a global event. There's this cloud of ions that comes to us is much bigger than the Earth. But some of it's very local because of the fact that it's on the sun side worse than on the other side. So, yeah.
Yeah. Do radio bursts have an effect on climate change?
That's a Nobel Prize question. No, there's a lot of evidence that it may affect space weather may affect climate, and the Mulder minimum is one of the clear evidence that there's a. However, the mechanism is not well understood and has been totally misunderstood for years. For many years, they believed that the cosmic rays form nuclei in our atmosphere on which condensation takes place. And it sounded very feasible and said, yeah, if we've got, strong solar wind, then likely we would have more rain and weather changes. But some calculations done by some colleagues at Northwestern University said, yes, that's possible, and it probably happens, but it is so minuscule, it's not really the thing that causes the change. One of the other postulates is that it is the change in the atmospheric composition because of these particles coming in, exciting the ions of the atoms in the atmosphere, changing the composition, changing pressures because of the different weights of the different species, that may be the driver behind climate and weather effects. And it's a working hypothesis at the moment, but we don't really have a good answer yet on whether there's a link. And the other problem is we don't really see this 11-year cycle in climate change, which would be a clear evidence that it's linked to the solar cycle and space weather. We've done that here in Hermanus. We've got rainfall records going back to 1940. Because we diligently measure the rainfall at Hermanus, and we've been supplying that to the local municipality for many years. And so we were looking for patterns in the rainfall and see what there's any correlation with the solar cycle, and we haven't found it yet. Peter.
There's evidence that you cannot use Hermanus data for rainfall because it's a full year rainfall area. The only way you can do it is in a dry area. And I've done an investigation with 3 rings in the southern part of Zimbabwe. And there you can clearly see solar cycle variations in carbon-13. The carbon-13 is a stable isotope. And wet carbon, well, it becomes a long story, but anyway, you see in the leaves, the leaves, when it's dry, the leaves, the openings close, and you get only an accumulation of carbon-13. When it's a lot of rain, then the leaves start opening up, and we get carbon-12 coming in from the atmosphere. And so by looking at the ratio between carbon-13 and carbon-12, you can easily see where there's a drought prevailing or whether there's ample of rain. So you cannot use Hermanus all along the coast region for those things, but you can clearly use it in 3 rings, which is a 1,000-year record that I have available, and they clearly show
Rainfall effect.
a rainfall pattern that is the 18-year one for Southern Africa, but you also get long-term solar periodicities inside your rainfall area, and that has been proven all over the world. But that is not climate change. Climate change is much worse than, for instance, cycles in the tree ring. The effect is too small. It's still prevailing, but the effect of hydrocarbons and fluorides in the atmosphere is completely overwhelming that signal. So you get climate change, because climate change is not strange to the world or the earth. You get for ice ages, and we are currently in a process of a peak phase of the earth. But it's, with most differences, it's happening so fast. It's much faster than before, and that is driven by man-made pollutants. So the effect of that more than you will still see, but it's too small. It's overwhelmed by the other effects.
Great. Thank you very much for that contribution.
Comprehensive answer there.
Yeah, no, Peter did some research on that, published a paper on that too. So
So at one stage I can give a presentation about it, but it's something completely unrelated or maybe small related to what you said.
thanks for the question.
Anybody else?
As a layman, I know nothing about this subject, but I just want to congratulate you on a really impressive talk. You spoke clearly, your graphics were brilliant, we could read them all. It was, you weren't speaking down to us, you were speaking to us, and we understood it, and it was outstanding, and you kind of took shape of the costume. So well done.
I love doing this, it's my lekker.
You can save us that picture because I would like to do
My sussie is 'n kunstenaar, sy hou van mooi prentjies.
So is SANSA an SOE?
No,
No, I was going to say, it couldn't be. No.
no, we are, what do we call ourselves now, a national key point. Which means we supposed to have the same security levels as ESCOM and some other national key points.
Yeah.
So if you come there, they're gonna get all of your details, your ID number and the car registration number, and make sure that you don't take anything out and so on. Yeah. No,
Oh, another secret to your success. The reason your ecolisto measurement was the one that was worked best for that last event was because your aerial was grounded in fables. There it was in amongst the rest. This was unique, fantastic, on a slab of concrete. Well done.
Okay, I'll convey that to John Moore. Yeah.
So could I just ask, I noticed that these sunspots move from left to right, from east to west.
Yep.
How long do they stay active for?
Aha, very good question. That's a very important observation because the sun rotates. Let me take this case, that one. Yeah. The sun rotates at its equator in 27 days. At the poles, it rotates in 33 days. So the sun is not a solid body. And one of the theories as to why these flares take place is magnetic contortion, because the equator rotates faster than the poles, and the magnetic field lines get stretched, and eventually they snap out into magnetic space. But these sunspots can go for several cycles. They are called Carrington rotations, after Lord Carrington that first observed the sunspots and the reflection of sunspots. So the best prediction of space weather 27 days from now is what we saw today. Because it's not a deterministic event. We don't know when the sunspot will flare and when the sunspot will appear. But some sunspots do last through several rotations. Sometimes by the time they've gone around, they've exhausted all their energy and they're not visible 27 days later.
Sorry, just another question. So if they come around, do they keep the same number?
No, they get a new number every time they appear. Yeah. But they can see what's going on the far side of the sun by two different means. They've got a satellite on the other side of the sun that looks at the sun. Originally, the satellite was one of a pair of satellites called stereo A and stereo B. The one was going to go slightly faster than the Earth, and the other one slightly slower than the Earth, so that they could see the sun from the sides, not just from the Earth's position, and see which direction these flares get in. Are they coming to the Earth or going the other way? Unfortunately, one of them was switched off when it went behind the sun, because we couldn't get the signals from that satellite as it traversed the sun, and they couldn't get it switched on again. So now we have only one of the stereo satellites that now sometimes is in a good position, sometimes it's in the same position as the Earth, and then goes around. So we've got a satellite that can see the sun on the other side, and we can see flares on the other side from that satellite. But they also use a technique called seismology, which actually detects they call it vibrations on the surface of the sun and then propagate the origin, like they will do seismic testing, explode something in a hole, and then take the propagation to some other point and infer what's going on in between. They use that same technique to use these vibrations on the sun to infer where it's coming from, and it's likely to come from sunspot region. So with the geoseismology, they can actually map the far side of the sun and tell us when a particular sunspot group will be coming around blowing the sun.
Am I correct in assuming that supernova are expired sun?
Ask that from Peter. I'm not an astronomer, so that may be a good way to describe it. I'm a novice if it talks about astronomy. I've heard about supernova. I can tell you what's the solar radio burst that's coming from a supernova. The largest supernova had a solar radio burst or sun radio burst in the order of 5,000 Janskis, because normally they measure the radio intensity from stars in Janskis. Typically, the radio emissions that they do with these, I'm looking for the word now, people. SKA, square kilometer array that they want to radio sonic, I'll keep that. Yeah, is on the order of a fraction of a Jansky. And Cassiopeia A, I think, was the largest known event in stellar space that had something like 500 Janskis, which is still well below any of our solar radio bursts, simply because it's so much further away. But I can't confirm your statement. Yes,
Can I just find out that solar flare that left on the 3rd of October didn't quite hit us when we thought it was going to hit us, but it seems to have, its effects seem to be more prolonged than anticipated.
it was a mystery. It was a mystery because all of the centers with which we communicated before we said there's a flare agreed on it, and we all sat waiting, and it just seemed like that flare dissipated. It never had the magnetic storm that we anticipated it would result in. So yeah, it's still a mystery. What happened to that flare? Some of the others, there's been lots of talk at a recent conference on, what happened to that X-class flare, because it just didn't manifest on the Earth, and they were so sure that it was coming our way.
How do you measure that?
They have. How do we know it's coming our way?
How do you measure that, and how do you miss that?
Okay. We can see the flare on the sun from the X-ray emissions and from the splash.
Just repeat the question.
The question.
How do you measure that, and how do you miss that?
Yeah. So we know there's something on its way from the sun, from the satellites that watch the sun 27 or 24/7. Yeah. However, those flares can pass above the Earth, below the Earth, ahead of the Earth, behind the Earth. But there is a satellite that sits 100th of the distance between the Earth and the sun at what is called the L1 point. It's where the gravitational attraction of the sun matches the gravitational attraction of the Earth. So the satellite can sit nice and still there, and it goes around the sun exactly the same time it takes the Earth to go around the sun. If the solar wind passes that satellite, we see a very clear increase in velocity of the solar wind. We see a clear increase in density of the solar wind, and that's so close to the Earth that there's no doubt that it will hit the Earth. And so what happened with this flare was we saw it from the sun, we saw the X-ray flare, and it never hit the satellite. It tells us it's definitely going to hit the Earth.
So it just got absorbed into that space.
Maybe I'll be able to tell you what's the story next year. Yeah, no, thank you for mentioning that. So, yeah, space weather prediction is still very much of a black art. I mean, if in weather prediction we think we can predict a few days and maybe weeks and sometimes months ahead, if we can predict 1 day ahead with space weather and be reasonably accurate, we're very happy. We do keep a record of our space weather predictions because we've got the 27-day prediction. So what we see today may happen again in 27 days. We've got the 4-day prediction. If there's a flare on the sun, it may hit us in 4 days. But then we've got the 1-hour prediction, and that's when it passes this satellite at L1, then we know it's going to hit the Earth. It cannot miss the Earth if it passes that L1 point.
And that's within an hour.
And that's within an hour. Yeah. So with our discussions with Eskom, we said we can tell you that there's a possibility that you got to shut down the network. But the real confirmation that it's going to hit us can only be given an hour. And sometimes not even that much. If it's a very
Are we going to get sun shading as well as load shedding?
If it's a very fast solar wind, it's as short as 20 minutes.
Yeah, what is the internal mechanism in the sun that creates a flare in the first place?
think I had a slide that shows that. Let me try and go back and change that. I hid that slide for the sake of time, but I know I've got a slide that shows that mechanism, or at least how they think it works. So if I get out of this and unhide that slide, how do I do this now? Go here and click. Does it? All right. So let me just go down to, okay, I've stopped that screen sharing. That's fine. Let me go back to my slides, which is this. No, that was the substorm slide. Have I now got out of my presentation? No, there it is. Okay. So I just want to get to the slide that shows that proposed mechanism. Does it? And then I just want to unhide this slide, which is this one. Unhide the slide. And then I will go to Zoom and share. Okay, then I've got to first go into putting this in presentation mode. And then go back to Zoom if I can. And sorry, go to Zoom and do this and share again the screen. Okay, right. And then somehow get rid of this stuff.
Just click on the top right there.
Didn't do it.
That's my meeting.
Yeah. So let's try that again. Okay, let me leave it there. So this is one of the formulations as to how this happens. The magnetic field lines below the solar corona protrude the what we call the surface of the sun, the chromosphere, yeah. And as this magnetic field, which is pervasive throughout the sun, protrudes the sun, we still have connection between the north and south pole parts of that magnetic field. So the sun has localized north and south poles. And we can see these magnetic field lines because of the high energy particles moving back and forth along those magnetic field lines with a magnetic bottle effect like you have in a cyclotron. So they are visible. And at times, these magnetic field lines open up into interplanetary space. Then we talk about them as open field lines. And they carry along the magnetic field lines the solar wind, because there's a phenomenon in space science that says this frozen in condition, where the magnetic field is, there the particles, the ionized particles go, and the ionized particles carry the magnetic fields with them. And so that's one of the postulates for the mechanism. There may be better ones. Peter may know some other.
Basically, what happens to magnetic field lines? Ejects the particles and they off they go into outer space.
Yeah.
That's in the long and the short.
Yeah.
Almost like a whip crack.
Yep.
Yeah.
But it's also a connection process that.
How much can you pick up from other planets within the solar system? Like Earth has this experience, we can measure, but now we've got satellites going to go to Europa around Jupiter and so on, and it's getting into their whatever's coming off the ice there. Will that send back information that also helps us understand the sun as well?
I'm not sure. We do know that there are aurora on other planets, because if a planet has a magnetic field and it has an atmosphere, it will be impacted in the same way that the Earth is. Whether that tells us more about how space weather is going to affect the Earth, I'm not sure. So there's space weather on other planets, that we know.
But they'd be beyond this anyway.
But I don't know whether they've got technologies on the other planets that are affected by the So maybe we can't call it space weather, because we reserve space weather for those events that have effects on technologies.
Can I ask a quick question? I'm running out of time a little bit. I was sent an article this morning actually from Australia about a very rare phenomenon called STEAM. They have this bright stripe up in the sky. I've never heard of that. Do you know
I've seen it for the first time on spaceweather.com, which is a good site to go and visit every day to see what's going on, because they have all of these interesting phenomena. They show you the sunspot, they show you the flares, they show the aurora. And there was quite a discussion about Steve, because it's not aurora, but it is some phenomenon in the atmosphere which emits light. I have heard the word, I don't understand exactly what it is. You know, Peter? Steve?
Which currents flowing in the magnetosphere. That's basically what it is. And exciting the atoms and ions, and then a piece of emission. But it's not space weather.
There are some other lights in the sky that are caused by satellites, Elon Musk notably.
He's a square word to astronomers.
Yeah, because not only because of the satellites that emit radio waves and kill our radio astronomy, but because of the emissions of the rockets that cause local ionization and then emission and so on. Yeah.
Anyway, last big stupid question probably. When magnetic waves around the Earth, is the Earth's gravity perhaps responsible for causing it to come back?
Gravity does not affect magnetism, at least not on the scale of our Earth. But there's no. Can we talk about magnetic waves? Yes, we can. But it is the background magnetic field of the Earth that is our shield. Because the solar wind carries the solar magnetic field, and the particles all sit on these magnetic field lines. And then the sun's magnetic field connects to the Earth's magnetic field on the sun side, and the magnetic field lines drag those particles to the tail side. So most of the solar wind gets diverted around the Earth. It's only at the high latitudes, they call them the cusp regions, where the Earth's magnetic field lines come down towards the Earth, because at the equator, the magnetic field lines are parallel to the Earth. But at the 60 to 70 degree latitudes, the magnetic field lines come into the Earth. And so if some of those particles find their way into the atmosphere, they get carried down along those magnetic field lines, and that's what causes the aurora. But the gravity of the Earth doesn't affect that.
Okay, we've slightly overstayed our time and whatever. The staff and so on, but questions and discussions very fascinating.